In the next part of this module, we're going to look at ionic solids and molecular solids, as well as covalent network solids, and some of the properties of each of those. Ionic solids, they contain a cation and an anion that are held together by ionic interactions between those two oppositely charged ions. Ionic solids, they contain a cation, which is positively charged, and an anion, which is negatively charged, held together by an ionic bond. Right, and so here would be our chloride, here's our sodium, here's our chloride, here's our sodium, here's our chloride. This is our ionic compound. We've got attraction between these oppositely charged ions, holding them together as this ionic solid. As you can imagine now, these are different than a metal because of this arrangement. These ions have to be held together by this intermolecular force, by these ionic interactions. As a result, they're very brittle, right? I need to hold these two together. I cannot pull them apart. I cannot stretch this material out like I treat a metal. They're very brittle. Again, because these electrons now are assigned to specific atoms, they're assigned to specific ions, the cation and the anion, they're not good conductors of heat or electricity. And they have high melting points. Very high, not very high, but high melting points. So there are some differences that ionic solids share from their metallic solids. They're brittle, they're not good conductors of heat and electricity because electrons are assigned to a specific location, and they have high melting points. The shape of an ionic solid is determined based on what are the sizes of the ions that are coming together, right? The radius of both of those ions that are coming together, and that's going to dictate the ultimate crystal structure that that material takes. And so, for example, if we have two ions that are of similar size, right, they can come together pretty easily, or if they have ions of two different sizes, that's going to change the arrangement and the shape that those two ions come together and how they pack together in the ultimate crystal structure of that ionic solid. So the ultimate structure of ionic solids depends on the ions coming together, right? What is their ionic radius? What is the ionic radius for each of those ions? And also, what is the charge on each ion, right? That's what we have to answer. Right, as the radius changes, you're going to change how those two different ions can pack together, or as the charge changes, that'll also change how things have to pack together. So for example, right, in our sodium chloride, it's a 1-to-1 ratio, but say magnesium chloride, where magnesium now is 2+ and chloride is -1, now that ratio is changed because the charge changes. So now I have to fit two chlorides around each magnesium in this ionic solid. Ionic solids are also different from metallic solids, the other solids we're going to look at, because they're brittle. They're brittle because if you apply enough force, and so if I push here and I push here, you can apply enough force to essentially break or fracture that ionic solid. So here are my ionic bonds between the sodium and the chloride. I can fracture that material because essentially you force those ionic bonds to slip. Once they slip once over, right, I've got a negative on top of a negative, a positive on top of a positive, and that ionic solid easily fractures, and it'll form a nice clean face. And so when we see those crystals of sodium chloride, right, they form those nice clean faces because sodium chloride crystal will cleave in a nice uniform way right down and right through the crystal structure of that solid. So they are brittle, because if enough shear force or stress is applied, the ionic material will slip one atom over and cleave along a uniform face. And that's why you can see nice uniform crystals of sodium chloride. Those nice uniform crystals of sodium chloride are formed because they're going to break in nice uniform repeating ways because it's an organized solid. Right? It's an ordered crystalline solid. We've got uniform order of repeating patterns, and so it's going to keep breaking in those repeating patterns, forming nice uniform faces. So that's how our ionic solids differ, right? That's how a crystalline solid is different from an amorphous solid. You can expect uniform repeating patterns of that ionic solid. The ordered crystalline ionic solid will break and cleave in uniform repeating patterns of very similar shape over and over and over again. Think of all the little squares, cubes of calcium chloride that you've seen. They're all going to break in uniform ways. Compared to an amorphous solid like glass, if you were to break a glass window, it's going to fracture in 100,000 little different pieces where no two pieces are identical because there's no uniform repeating pattern of the structure of an amorphous solid like glass. The next solid that we're going to talk about are molecular solids. Let's think about molecular solids, right? Molecular solids are a little bit different because they're molecules that are held together. Molecular solids are molecules that are held together by intermolecular forces. And so what do you think that means for the properties of a molecular solid if they're held together by intermolecular forces? Do molecular solids have a higher or lower boiling point than an ionic solid, for example? Well, our intermolecular forces, like London dispersion forces, dipole-dipole forces, and hydrogen bonding, those are all weak forces relative to covalent bonds, relative to ionic bonds. So as a result, our molecular solids, they tend to be soft and have low melting points. Right? One example of a molecular solid is ice. We know ice has a melting point of 0 degrees. Ice is a molecular solid because it's a bunch of water molecules held together by hydrogen bonding within that water sample. So it's a molecular solid because the only thing that's making it a solid is the hydrogen bonding holding individual molecules, right? In this case, molecules of water, holding those individual molecules together. That's drastically different than a covalent network solid. Covalent network solid, like diamond, those atoms are held together by covalent bonds. Right? Covalent bonds are much stronger than intermolecular forces, and as a result, our covalent network solids are incredibly hard materials. Right? Diamond is one of the hardest materials we know. Not only are they very hard, they have incredibly high melting points. And just think about the differences in those properties between covalent network versus molecular solid. Molecular solid held together by weak intermolecular forces. Covalent network solid held together by covalent bonds. Very strong forces between those atoms of carbon make for a very strong material. So here's another comparison of covalent network versus molecular solids, some of the differences in their properties. So graphite, even though graphite contains carbon, just like diamond contains carbon, graphite is actually an example of a molecular solid. You have these individual sheets of graphite, and this is just carbon. So they're held together by London dispersion forces, right, holding each of those layers of graphite together. But it's just a different form of carbon. It's just a different bonding arrangement for carbon. So as a result, graphite, and think of your pencil lead, right? Graphite is very soft. It's very malleable. And so think of how soft that is. Essentially, when you're applying your pencil lead to the surface of a paper and you're drawing your pencil lead across that paper, you are applying enough of a force to separate these individual layers of graphite. And that's what you're leaving behind on the paper. You're leaving a trail of graphite, right, that you've separated by pulling your pen across the paper or pulling your pencil across the paper. So these molecular solids, right, they're very soft and they're very easy to separate because they're just held together by London dispersion forces, weak intermolecular forces. Interesting side note of graphite. Graphite has some really interesting properties with respect to its conduction. And so there was a lot of research for a while on how to isolate an individual sheet of graphite, so an individual layer of graphite. And the researchers that won the Nobel Prize for this research and actually ended up isolating very thin layers of graphite, they actually did this research with, you guessed it, Scotch tape. They took samples of Scotch tape and applied it to the surface of graphite, and they were able to pull off very thin layers of graphite from that surface, of graphene at that point. But very interesting to think about, of all the money that's put into research and how we were able to isolate graphene, which is an individual layer of graphite, was simply Scotch tape and some pencil lead. Okay, so here's a question for you. We have a solid with a very high melting point. It's very hard and a poor electrical conduction. This is an example of what type of solid? Well, there are a few things we can rule out, right? It says that we have poor electrical conduction. So immediately we can cancel out metallic solid, and we can also cancel out choice E as well because that contains metallic solid. Those are great conductors of electricity. So high melting point, great hardness. We can also cancel out molecular solids because those have low melting points and they're not very hard. So now we're left with ionic solid and covalent network solid. So I would go with covalent network solid in this case because covalent network solid is going to have a higher melting point than an ionic solid, and it'll also be harder. We cannot simply cleave a covalent network solid. We can't just simply break diamond in half the same way that we can cleave and break an ionic solid in half. So I would go with choice D for this question. But you should be able to compare and kind of understand the different properties for all four of these solids: ionic, metallic, molecular, and covalent network solids. Which ones have high melting points? Which ones have low melting points? Which ones are strong? Which ones are malleable? What are some of the properties of each of these molecular solids that we've talked about?